welcome to the DigitalOcean Amsterdam meetup. I don't have my speaker notes on here, which does not help. There it is. Right. Yes, welcome. This is February. We didn't do one in January because I was super lazy. I was watching my money disappear in crypto, so hence we didn't do one in January. But it's February, so that's great. This is a special one because we've got two internet pioneers here, hopefully to tell us how the internet works. Yes, for those of you who haven't done DigitalOcean Amsterdam meetup before, we do monthly meetups. They're super chilled. We have newfangled technology every time, like speakers and microphones. And yeah, usually there's beer, there's drinks, like free stuff. Like it's super chilled, and we don't do recruitment stuff because we don't want that. Yep, I think that's all I have to say. I also have a clicker now with a laser. For those of you who don't know who or what DigitalOcean is a hosting provider. They make it super simple to get websites and all things, servers up online. This is what it looks like. The UI is really nice, much more simple than our competitors. I don't work for DigitalOcean, by the way, but still, it's still great. Yeah, so they make it a lot easier. So instead of being like super angry that you can't get your server to work because servers are hard, as we're about to find out with these guys, servers are hard. You can focus on all the good things like drinking beers and cat memes. Yeah, so how this meetup came about, it's kind of special. Normally I send lots of emails out to lots of DevOps and cloud-related speakers, but this one's kind of special. I read a book once. I actually have the book here. I don't normally advocate reading books because they ruin films. But this one was kind of good. So I read this book and it told me about how the internet works, and that was really interesting. I then went to the AMS-IX launch, which is a data center. You should go in the science park. It was pretty empty, but now it's full of service, so that's great. Back to the book. And yeah, this book had these two people in it. And I thought, well, maybe people would be really interested about how the internet actually works. And as it turns out, people in books sometimes exist in real life. So I sent some emails. Yeah, Henk actually has a LinkedIn profile, which is great. So I could just send him an email directly. It's Kees. Kees, yes. Kees doesn't have a LinkedIn profile, so that makes it a little more difficult. So he's actually on the Internet Hall of Fame. He's a big guy. Yes, I sent them an email and asked them to pass it on. And amazingly, they did. And then I got a reply from him literally the next day. And we had some chatting, and he said he'd do it, and I am eternally grateful. So yes, that's how this came about. A few people, you can't see Erica's name, but there's a few people that helped make this meetup happen. Hugo, most notably, he is my audio engineer. He's also the Livestream guy. He makes coffee. He does a lot of things, so that's good. Erica, you saw at the front door, she does check-in. She's the smiley face of the operation. And Sharon is the wine tasting guru. She approves all of the wine that you might be drinking. And she pulls those kind of faces when it's terrible wine. So she did the tasting so that you don't have to. So that's really good. Yeah, a word from our sponsors. So we've already gone through DigitalOcean. They are paying for the beers, and it's pizza, I'm afraid, guys. I tried not to do pizza, and we tried to do like nachos, but it's too expensive. And you can either have like half a pizza, or you can have like 3 nachos. So it's kind of like maybe they'd want half a pizza. So that's what we've gone for. You've got like quantity over quality. So yeah, I keep trying. If you guys come up with anything better on the food front, then let me know, and I'm more than happy to do something that's not pizza, because everybody does pizza. But yeah, next time maybe. Yeah, Your Majesty, this is the Your Majesty office. I work for Your Majesty, not DigitalOcean. We do websites, basically. They really need to give me the official brand spiel, but apparently we do websites, and that's great. Yeah, we do websites for big people like Netflix, Adidas, Samsung, yeah, Universal Music Group. This is the Samsung website. We also do like their on-brand experience, like on the TVs. The website works on phones. It's great. And we've done stuff for Adidas. We did these huge cubes. They had some new shoes out, so we like put shoes on the side of big boxes, and Everybody loves shoes, so that's great. We put them all over Amsterdam, all over Europe even. So that's good. And skiing. This is Rotterfeller. They do really great ski stuff, and we rebuilt their website, and now it looks amazing. So that's also good. We also do machine learning stuff. We don't have a slide for that, but machine learning with eye tracking, that's new. It's very exciting. And this is what we look like. We went on holiday, and we all have silly faces. There's girls and guys, which is great. We're a big team. And yes, so back to tonight's meetup. Yeah, so you hopefully found a seat. That's good. And this is the introduction. Henk is next up, straight after this. He's talking about the Amsterdam Internet Exchange peering.
Yep.
Like, yeah, he does a better introduction than I will. We then have a break. You can get yourself more beers. There's soft drinks. There's wine over there. Grab yourself a stress shark if you're feeling really angry. Then, yeah, Kees. Still don't know if I'm pronouncing that right.
Kees Neggers.
Yeah, I'm not going to try the second name. Yes, he's going to do like I got his slide deck and it looks fantastic. So I'm really excited for that. I'll introduce that later. And then straight after that, we're going to do pizza, and yeah, we can just chat. And yeah, we're here until we get kicked out. So you can just sit and chill, get quietly drunk. That's great. Emergencies and toilets. I probably should do toilets as well. Toilets are just behind you through the door. Yeah, that's self-explanatory. Emergencies, hopefully you won't need it. If there's a fire, you can scramble through that way, and there's a fire exit just over there. And that you go down the stairs. We all congregate at the bridge. If someone hurts themselves, we have paracetamol. Hugo is an emergency person. You're trained in this.
That's true.
He can patch you up. So that's good. Hopefully, you won't need that, and it'll be totally fine. But we just in case. We have a code of conduct as well. I'll just read it. So DigitalOcean is dedicated to providing a harassment-free event experience for everyone, regardless of gender identity and expression, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion or that thereof, or technological choices. Basically, we're just nice people and be nice to each other, and we will have a good night. And if anybody has any issues, we have procedures, and I've got contact details for anyone you may meet. But hopefully, we won't need that. Just chill, and we just be nice to each other, and that's great. Yeah. So I've already booked the next couple of meetups. Next month, 22nd of March, we're doing machine learning. So yeah. So we're doing identifying traffic lights using machine learning, and then we've got guys from Picnic coming back. They are doing beyond machine learning, augmented human or intelligence for the supply chain of the future. So that'll be really interesting. Yeah. So then in April, Picnic are coming back. They're going to tell us about their DevOps and how they work with Kubernetes. And I've got a guy who's come back. He actually won't come to this meetup. And he's going to tell us what Kubernetes actually is. So we do them in different order. See what is Kubernetes and then how to use it for multi-site deployment. Sounds like a great idea. Yeah, and then that's me done. If you want to harass me on Twitter, my tweet handle thing is there. Samantha runs the DigitalOcean events internationally, so if you want to say nice things or mean things like, oh, it's tasty pizza, you send them to her. Use the hashtag DOMeetup because that helps. And if you want to send something more private, you can do samantha@digitalocean.com, and she's super friendly, and she'll get back to you. So that's really nice. Right, that is the end of my bit. Does anybody have any questions? No. Okay, that's great. Okay, so I have an intro spiel for Henk. So Henk is a pretty knowledgeable guy. He studied astrophysics and mathematics and theoretical physics at the University of Amsterdam, and he has a bachelor degree in marine engineering. So you can tell us about fish.
No.
But the main reason why Henk is actually here, he works for the Amsterdam Internet Exchange. He joined the Amsterdam Internet Exchange in 2001, and before that he was on their board. What else did he do? Prior to working at Amsterdam Internet Exchange, he was the director of Internet Working Center of Expertise at AT&T. And then before that, he was the senior network architect. This is all on the meetup page, so if you want to reread it, you can go to that. And then before that, he was the network operations center, working with SurfNet, which is where Kees comes from. Yes, so I'm sure you've got a much better introduction spiel than I have. Let's get you up here, and then you can do your thing. Good stuff. Are you on my computer?
Yes.
Good. Whereabouts are you on my computer?
I've no clue.
Yes, this guy. And then we just play. Do you need notes?
That's going to be.
That's fine. Good news. Okay, I'm going to give you this. Yeah, that's you. Good work. Fancy transitions. You may need to hold it in front of your face. Does it work, Hugo, with the microphone?
Trust it.
People in the back hear me?
Okay.
Okay, cool.
Type. People on the internet.
Well, good evening, everyone. It's an incredibly large audience, much larger than I expected, but so much for the better. Really like that. I'm very well introduced. I'm Henk Steenman. I got involved with the Amsterdam Internet Exchange back in 1996 when 20 ISPs wanted to more formalize what was already existing in Internet Exchange, among others, set up by SurfNet and Kees Neggers as an interconnection platform for the academic IP networks and the then starting to exist new Dutch internet service providers. So during 1996 there was this intention to more formalize that, and together with 20 ISPs in January 1997 they established what was called the Amsterdam Internet Exchange Association, and that association outsourced management of the exchange to SurfNet until roughly 2000, when it became a pretty big thing. We were not 20 ISPs anymore, but if I remember correctly, around 100 at that time already. And Amsterdam Internet Exchange established a limited company under the BV to do the operation of the exchange. But the articles of the AMS-IX Association are pretty interesting. So the articles are, the objective of the association is to facilitate the exchange of internet traffic in the broadest sense of the word. Specifically at that time, certainly in the Netherlands. And they did that by on a non-profit basis. And the association at that time tried to achieve that by connecting their members to the Amsterdam Internet Exchange platform, which I will talk about later, to facilitate that exchange of internet traffic. Then in 2000 we established the Amsterdam Internet Exchange Limited Liability Company, or the BV as we call it in Dutch, with only a single shareholder, which was the association, and the same objective as the association. So a not-for-profit company. Doesn't mean we don't make a profit. Actually we do. We actually every year we make quite some profit, but we give it back in the form of lowering access prices and investment in the platform to facilitate growth we see. Yeah, so that's about the company itself. At the time we started with around 6 people. We're now 54 I mean, and we have roughly 23 nationalities employed, among which Igor is one. And yeah, it's a very interesting and very dynamic company to work. But what is Amsterdam Internet Exchange? And for that we have to go back to how the internet is actually built up. And I don't know if you realize that, but the internet is actually all about interconnection. And what this picture shows is what we call a meet me room in a data center, which facilitates interconnection. I'll come back to that later. But this is a picture a colleague of mine made, Stefan Bakker, but it gives an idea of how the internet is built. You have all these different companies, I think roughly around 50,000 or 55,000 worldwide. All these companies you can visualize as a cloud, a network in itself. And within this network, all these companies can do whatever they want. It's their network, they can do their own thing there. But to make it the internet, to make the internet what it is, it's actually interconnecting all these different networks. And to do that, they need to operate according to a couple of rules. That is using IP addresses, IPv4, IPv6 addresses, and using a protocol called BGP to tell each other which addresses are reachable in their cloud. So to make the internet, it's all about interconnecting all these different clouds that represent these networks. So typically when you're at home or when you're in your office, you don't realize that, but what you typically see is something like this. You hook up your computer on your desk, your company is somehow connected to an ISP, or at home you have selected an ISP yourself, and that ISP takes care of connecting you to the rest of the internet. You don't have to think about it, you just type in where you want to go, typically a name that somehow gets translated to an IP address, and then your ISP knows how to route that to the IP address on the internet. And the way back, where you go, the content here knows from the source address you sent where to send it back. So how does the ISP establish this? How does the ISP accomplish this? That's where the interconnection part goes back to. And when you go back to the beginning of the internet, certainly, you could see something like this. You had like a hierarchy of network operators, some very large ones, which were indicated as tier 1 operators. And they had typically like a global reach. They were, I don't know if you know the names, but there's companies like Telia or AT&T or Verizon. They have a very big reach, and together they can access almost any address in the internet. And at a little bit lower layer, you have the more regional ISPs that cover an area like Europe or the US or a country in Asia or something. And the really local ISPs that operate typically on a country level, like KPN in the Netherlands or Access for All. And the way all these networks reach each other is by buying connectivity from one of the ISPs at a higher level. And of course, there's a commercial relation there. But in this model, the interconnection goes something like this. When you have ISP8 wants to access a computer or communicate with a computer in ISP9, it follows the interconnection that ISP8 has bought with ISP5 to get there. Or even in a more worst case, if he wants to connect to ISP10 here, it goes all the way up to this ISP3 and then back. In the beginning of the internet days, we had some situations where two providers in the Netherlands run into situations like this, and your packets were all the way routed to the US and back. And one, it costed a lot of money, and two, the efficiency of the routing and the path your traffic took was really long and really inefficient. So these relations in this way of interconnectivity is what's being called transit, and it's something like this. ISP11 buys connectivity from ISP12, so ISP12 makes sure that it gives reachability to ISP11 to everybody in the internet. It does that by advertising basically all the IP addresses that exist in the internet to ISP11. And ISP11 advertises the addresses in its own network to ISP12 to be advertised to the rest of the internet so they can find ISP11. And well, that's transit interconnection. Now, this is not really perfectly optimal, especially not when you have a couple of ISPs that are very close together. For example, in the same data center or in the same campus or whatever. And you might very well directly interconnect these ISPs to handle the traffic on a direct connection there, like for example over an internet exchange, or over a direct connection between the routers of these ISPs. So in that model, the same interconnection that we saw earlier would be like this. ISP8 directly connects to ISP9 over a local infrastructure, either a direct cable or some, for example, an Ethernet infrastructure, and ISP8 goes to ISP10 like this. So you've accomplished two things in this way. One is the performance of the interconnection is much better because it's very local. You don't have to traverse all kinds of long geographical distances or go over different networks. And every piece of traffic that's exchanged directly between these networks, you don't have to buy from the upstream or transit ISP. So you save on cost.
Excuse me, can I interrupt you?
Sure.
But it seems to me that then the exchange plays the same role as one of these ISP5 or 6.
Yeah.
Is that true?
True, but as I said, I've drawn here to be an exchange. You can also just put a direct fiber in between. An exchange is just an optimization. We'll come back to that later. Yeah, and typically, and that's of course what it becomes all about, is an exchange is a not-for-profit organization. We're way, way cheaper than whatever happens there. These relations, direct relations between these ISPs is what we call peering. In peering, the interconnection between the ISPs does not give you access to the rest of the internet. It only gives you access to the other network's customers. So again, ISP11 and ISP12. ISP12 only advertises the addresses in ISP12, and ISP11 only advertises addresses in ISP11. So these two ISPs in this model can reach each other's customers, each other's machines, but they cannot go beyond that. For that, they still need to buy transit from another ISP. And this is what's called peering. And peering is typically something that an internet exchange offers. And that is facilitating these direct connections between networks. And it's typically implemented something like this, big Ethernet switch. You have all these ISPs connected. And what you can also do with a direct connection, a fiber between two ISPs, it's a little bit more efficient if you have one connection to an Ethernet switch and can directly connect to all the other participants in the same Ethernet environment. So there's an optimization also. And like on AMS-IX, we have 800 connected parties. If you would have to implement that by direct connections, you would have 800 square, roughly, connections to make. Again, how do these networks talk to each other with a protocol called BGP? And what BGP basically does is tell the other network, I have these IP ranges behind me, and if you want to send traffic to these, put it in your tables and it gets to me and the other way around. So peering, the exchange of traffic between parties where only each other's customers are advertised. Peering in fact means equal party, peers. So you see peering at different levels in this hierarchy. The big tier 1 operators peer with each other, typically not over internet exchanges, but they interconnect. Peering often, but not necessarily, happens without financial settlements, because it are equal networks. Both parties have an equal gain from the relationship. That's, by the way, changing. And the benefits of peering are a reduced need for connectivity, lower cost, and optimization of your traffic streams. Yeah, well, that's basically the same. Peering arrangements, that's an interesting thing. So how do you, it's become a whole industry about all these networks arranging these agreements to set up interconnection. They're usually arranged on a bilateral basis, so one representative of a network goes to another representative of a network and says, hey, shall we peer? And then they set up a BGP session. But with 55,000 networks, I mean, that's quite a hassle. You have to talk to everybody. So you see all over the world special events where peering coordinators get together and make these arrangements. And I've met a couple there. And what you also see commonly on an internet exchange is what's called a route server, where people actually dump all their IP address ranges on a server, and every participant get that from that server instead of setting up these bilateral BGP sessions. Okay, well, peering typically happens in what's called a co-location data center. So this is Equinix AM5. When you see this, when you drive along the A2 richting Utrecht, you see this. You have the round hotel, and then next to it you see these gray boxes, which is this. It's a 13,000 square meter data center. And with data centers, you have to realize that there are roughly two kinds. You have the big compute centers, where all the servers are humming and computing everything that needs to be done to offer content on the internet, so the huge Google or Facebook data centers. And then you have these co-location centers where all these networks co-locate, host their routers together to make the interconnection between these networks. So it's a different concept than the big, huge server farm data centers. This one is in the Netherlands, 13,000 square meters. This one is one of the largest in the world. It's in Chicago, which is 100,000 square meters. And it's mostly filled with routers, and relatively very few servers. It's an old telephone book printing building, so it's huge, massive, and it can have lots of weight, etc. Meet me room, typical part of a data center, is where I have my router here, I pull a fiber to the meet me room, you have your router there, you pull a fiber to the meet me room, and in the meet me room there click together and you have a physical interconnection. So, well, this is a very neat one, but that's can show other examples. It's a little bit more messy, but yeah. And this is typically what an AMS-IX implementation looks like. It's just a couple of racks. In there are a couple of Ethernet switches, and there's lots of blinking lights and yellow fibers. So AMS-IX itself, one of these internet exchanges, we have facilities like that in 14 data centers in Amsterdam, a little bit distributed over the city. We also have an office very close by here on the Fredriksplein, but we don't offer any services there. It's just offices. And then our network looks something like this. It's basically a core spine network. We have 2 data centers where we have the core of our network located in 2 different data centers for resilience. And then in each data center we have a pair of access switches. A special device for resilience that offers resilience is an optical access switch. And then we have the customer router. So each pair of blocks here is located in a data center. This is the row for high-speed access, which is either 10 or 100 gigabit Ethernet, and this is 1 gigabit Ethernet access. In the network, we basically run 2 protocols. In the core, we run MPLS, VPLS, and on the edge towards the customer, we just run Ethernet. So for the customers, it's basically an Ethernet VLAN. But for us, it's a VPLS instance that emulates an Ethernet VLAN. And then all these connections here are dark fibers. It's just fiber through the city that we light up with different colors, each color representing 100 gigabits per second stream between the access sites and the core. That's basically our platform. Now these optical access switches are kind of special. So what we thought is these Ethernet switches are actually not super reliable, definitely not a couple of years back. So what if we have 2 and we give the customer router access either to one or the other in case there's a problem here or in case we need maintenance. So we found this device, which is basically a set of mirrors like this. Mirrors etched on a square of silicon, and you can move these mirrors with an electrostatic field. And by doing that, you can direct light that comes in on a fiber, falls on these small mirrors, you can direct it to go out on another fiber. So customer router sends light, the optical access switch decides to which of the access routers the light goes, and then the traffic goes on. And in case we have an issue, we just switch the mirror to another position and the light goes to the backup access switch. In that way we have realized an incredible uptime and availability of the platform. Don't know what that is. Okay. AMS-IX started in Amsterdam. We call it the Amsterdam Internet Exchange. Over time we got requests from other countries like, can you help us out here, can you help us out there? We are interested in internet exchanges like that, so we're now in 3 locations in the US, on the Caribbean, on Curacao, in Mumbai and in Hong Kong. Not so big as in Amsterdam, they're more relatively new. But basically we do the same thing there. And these are all local instances. So the exchange there is for the local traffic to be handled between service providers. There's no interconnection. Who connects? Now, well, basically everybody that does business on the internet. So transit providers, cloud providers, gaming companies, etc. We do different kinds of services. 98% of the service is just internet peering between service providers. But what we also do is peering between mobile operators to enable roaming. You might know, but how that works is when you go abroad with your mobile phone and you get to a network abroad, then you have to be authenticated with your home network, before you can have your 4G connection in the other country. Handling that authentication goes over so-called GRX providers, and interconnection of these GRX providers is also on AMS-IX, which gives us a well, quite crucial position in the roaming business. And when roaming became free in Europe, we saw an incredible increase in traffic there. And then we have some other products that are, well, all related to the same thing, like closed user group, which is basically another VLAN. Which one is this? Yeah. So this is the traffic we ship. So 10 years ago we were roughly at 2.6 terabytes per day, and now we're at 37 exabytes per day on traffic. And when you see the peak of the traffic, we are in 2017, we grew to 5.5 terabits per second. And the daily traffic profile looks something like this. So we're a little bit below 2 terabits per second in the morning. We grow to a little bit over 5 in the evening, and then it goes down. Roughly the same every day of the week, except on Sunday, then it goes up very fast in the morning, is flat for the rest of the day, and then goes down again. Everybody's doing the internet. Typical customers, well, basically every big name that you can think of that operates in the internet is there, especially the large ones and then the more local ones and the European ones. Companies also from Asia, from the Middle East. 820 parties at the moment.
May I ask, was that by size of your business review? I'm just looking at the size of the different.
I think that's just a marketing thing. I don't think it represents anything. No, I don't think so. But yeah, I can see why you think that. Yeah. So, yeah, that's about it. Interconnection, that's the basis underlying the internet. AMS-IX plays a major role in there, especially in Europe, where we facilitate that interconnection. So interconnection can be optimized and can be very economical. And we do that for a long time, and we plan to do it for a little while longer, unless Kees is going to tell us that we have to completely change that in the future because the internet is going to change. But it's questions. Yeah.
You said that the relationship is equal, but it's changing right now. That now there is, like, you know, different relationship, and one side is gaining more than another one. Can you elaborate a bit more on that?
Yeah. So the thing is, when you look back 5 years in 5 years time and before, the internet consisted of many small companies. Like in the Netherlands, you had many small internet service providers, right? Now you basically only have 2 left. So you can see what happened when you get concentration of power. Let's keep it at that without calling names. But that's basically what happens. Yeah.
So the inequality that come in is, I understand, financial. Like some companies have stronger position and they try to negotiate, like getting payment from other companies. That's what you meant.
Yeah.
Have you noticed that so the internet now versus the internet 5 years ago, is there any like change in the type of traffic that you're handling?
Yeah, well, definitely. I mean, you can know for yourself. I mean, it's all, I think, half of it is video.
Right.
I think that's definitely way more than 5 years ago. I mean, I think then the big video explosion was starting. So, yeah, definitely a change in traffic.
Yeah.
Yeah. Yeah.
I was thinking when I type some URL, is there a way I can see how that request travels?
Yeah. When you log in on a terminal on your computer and you have an application called traceroute,
Yeah.
You can basically see which IP addresses are traversed to your destination, and then you can translate these IP addresses back to a network name by a reverse DNS lookup or other means. And in that way, you can see which networks are passed before you reach your destination. Yeah. So the name is for the application is traceroute, TRACE route. Yeah.
I'll check that. Thank you.
Yeah.
Oh, I was wondering, as a company, you operate only on the physical layer of the OSI, right?
Yes.
You don't dive deep into packets and analyzing, like, for
No.
example, the content and everything.
No, that's
So,
strictly forbidden by the association.
it's forbidden by you guys, so.
Well, it's for
Yes.
well, so the association controls the internet, right? Through the board. That's both a member that both represents the association and the limited company. The members of the association have told us many times you're not supposed to look into the traffic. And we have no reason to do so.
Who's on the board? Like what kind of
at the board, at the moment, the chairman of the board is a woman working for Google. There is someone working for, well, yeah. Yeah. There's someone working for LeaseWeb. It's you might have heard of LeaseWeb. There's someone working for Bix, the Belgian big carrier. There's someone from BIT, which is a small Dutch data center company in Arnhem. And there's a person working for Megaport, which is a transport provider in Europe. So it's quite diverse, but yeah.
Your operations overseas, say in the United States, how different is that from what you provide for here?
No, it's not. It's not different. It's basically the same.
And so, is it just the company's expertise that has got you over, or is there some benefit you get from having a non-local person constantly here?
So it's interesting. So when we go back in time a little bit, then in Europe, typically interconnection at the local level was implemented on internet exchanges. In the US, interconnection was typically implemented by direct connection between operators. So, and that was very much concentrated in a number of data centers of the same brand. So the interconnection landscape was mostly in a couple of big data centers implemented as direct connections. So there were a lot of operators who were unhappy with that, and they saw the European model like, hey, this is also working and it doesn't bind us to a specific data center, because as you saw, we are present in many different data centers, giving our customers choice where to co-locate their equipment. So they can negotiate price and everything and have it independent of the interconnection. So that's why they invited us from, why don't you want to try your model in the US and see if that works. That's how we ended up in the US. And the same for India and Hong Kong. Okay.
Just one more question, and maybe I missed that, but the interconnection between your data centers, are there any connection between them? Or?
Yeah, definitely. So the lower layer is the customer routers. They connect to the AMS-IX access switches, right? And then each of these access switches is in a different data center. So to interconnect all these data centers, I can put a blue square over each of these pair of switches here. To interconnect them, we have these connections through the city to the core of the network, going to all the other data centers, to all the other switches.
So each one is connected to every other one.
Yes. Yeah.
And how wide is the area that you cover? Is it like Amsterdam and
This
neighborhood, or is it
no,
like
it's
Netherlands?
Amsterdam and Haarlem.
Oh.
Yeah. So we got at the time, a long time ago, we got the association told us you have to provide this only in Amsterdam because we don't want to compete with the carriers. That was a long time ago. So then we got a request from a data center in Haarlem, like, can you connect us to your network? And then we considered Haarlem to be the greater Amsterdam. So we still fulfilled the requirement. But, yeah.
Do you expect it to grow, or is there like technical limitation to how wide can it be?
No, there's no technical limitations. It becomes a little bit more expensive if you go longer distances. But what we prefer is to work with partners who can bring us to other data centers in the Netherlands and have connectivity to them. So we don't have to invest in our own network going there. And that's a more scalable model, even going beyond Europe or beyond Netherlands.
Do you own the pipe between data centers? The physical connection?
The dark fiber here is leased from a company.
Right.
Yeah.
And the connection between, like, let's say, Caribbean and Amsterdam?
No, there's no connection.
Oh.
It's what I think what I told. So each of these exchanges are entities on themselves. So they handle local traffic from local operators, and they're not interconnected with Amsterdam.
In Caribbean would go through tier 1 ISP. If I connect to a server in Caribbean, then it will go through ISP.
Probably.
The big one.
Yeah. Yeah.
And typically in Europe, let's say that I'm connecting to a server in, well, let's say in Poland or in Czech. Is it going through this tier 1, or is there some European?
It depends, because many Polish operators have also connected their networks to M6. So you might go directly to the Polish operator here on M6, or you might go through one of these transit ISPs. But it depends on the operator.
Yeah,
how many internet exchanges are there in the Netherlands?
In the Netherlands, there are a couple. There's M6. We are the oldest and largest. And then KPN has its own internet exchange, which they call the neutral internet exchange. And then there's a couple of very small ones that mostly handle local Dutch traffic, local Dutch operators. Okay?
That's about it. Okay, cool.
Okay.
Can we, Right, okay, so we've got about 8-10 minutes to grab a beer, and there's drinks, go to the toilet and stuff. Henk, are you going to be here all night?
Well, I'm staying here at least for case after case.
Nice. So if you have any other questions, you can always ask him now or during pizzas. expertise, leadership, and coordination activities have made him one of the key figures in the development of the internet in the Netherlands and around the world. He joined the world of international research and education networking in 1984. So that's 6 years before I'm born. And when he became the European Academic Research Network Director for the Netherlands. He did this from 1988 and he retired in 2012. And yes, he did some great things. And I'm just going to surmise because this is really huge. He did loads of things. He's always been a strong advocate for the principles of open, inclusive, and bottom-up industry self-regulation. These principles affected loads of organizations, including the Amsterdam Internet Exchange. In 1991, he was leading the effort to create EBO, the first European internet provider backbone, based on the concept of open exchanges. What else we got? IP turned out to be the superior solution, and it finally settled the protocol wars and paved the way for a commercial introduction of the internet in Europe. With SurfNet, he pushed the envelope again in 2001, introducing 10 gigabits per second in IP networking directly over 10G DWDM optical waves. That sounds pretty impressive. As long as I can view my YouTube, so it's very quick. I'm sure I can thank you for that. But yeah, either way, he is a really big guy, and he's done some great stuff, far more than the paragraph he sent me. And yes, you're here to talk about the past internet and how the internet's going to change in the future. If we can all give him a warm welcome, that'd be amazing. Amazing. I will sort this out. And then this is you, right? And then we hit play. And there we go. So yes.
Thank you. Thank you, David, for inviting me here. It's a pleasure. Is it too loud? Okay, it's a pleasure to speak here for this audience.
Keep going.
Okay, is it my?
Yeah, let's move it down. Let's move it down.
Is this better? Yeah? Okay, thank you. So I was asked to compliment Henk Stark and giving some historical reflections, and I said, okay, that sounds good, but just history is not good enough for this community. So I will try to link this historical development towards the future. So the internet is best described as a wonderful accident. It was designed as a network for researchers in the 60s and 70s, and we started to use it in the 80s. But now it's an essential infrastructure for the network society. It's changed society. We have a different society since we have the internet. And so this is remarkable. So how could that happen? And then the next question, is the current internet future-proof? And of course, you can guess already, not in my view. So we have to do something about that. So let's start then with how the communication networks evolved. Well, the first network that started in the end of the 19th century was the telephone network. It was circuit switched over twisted pair copper. It was connection oriented. You had to set up a connection before you could use it. And it focused on the pass. So you created a pass between one end and another end, and then you started to talk. It was designed for voice, and voice only initially. And the net was the service. So there was not an operator and a service provider that provided services on top of that. It was one and the same. Actually, the telephone handset was part of the network. And up to, I think, the 70s, in the Netherlands, it was even impossible to connect anything else than what was delivered by the PTT itself. So this was one of the problems. You couldn't connect a modem to it because you are not allowed to do so. That's why we got acoustic modems. So you could still use the network because you pretended to be a voice connection. So this is all history, of course. But of course, this all needed a central setup, and for computers which were emerging in the 60s and the 70s, this was not a good solution. So something needed to be done about that. Before I go in the data communications, another important network is cable TV networks. They were specifically designed for broadcasting from one place to many other places. And the technical solution for that was optimized for that purpose as well, of course. So again, this was not automatically a network that you could use for two-way connection between computers. So we needed something better, something digital and computer ready, and that became the internet, of course. That is no longer a circuit-switched network, it is a packet-switched one. It is currently based on TCP/IP, and it focuses on the endpoints, not on the paths. So it is an end-to-end network. And very important, as you will see later on, it has no central management. So packet switching, of course, didn't exist in the 70s. So it needed to be invented. And the first ideas started in the 60s by Paul Barron in the US. He worked for Rand Corporation, and by Donald Davis for the National Physics Laboratory in the UK. They were the ones, independent of each other, who said the phone network is not good for our computers, we need something different, and they suggested packets to do that. And the first demo of an open access packet network became ARPANET. This was in 1969. And it was based on the ideas of Donald Davis. So actually, the initial ARPANET was based on UK technology, or UK ideas at least. But of course, it was built with the big money and the big power of the ARPA in the United States, who really wanted a better infrastructure for interconnecting the different researchers who were scattered around the United States to the supercomputer centers they had also in a few places in the United States, and they wanted to have a better collaboration between these researchers, and they saw a computer network would be a better solution for that. But this is important, the initial ARPANET of 69 was a connection-oriented network. It was not connectionless. And it had a connection-oriented subnetwork that created the connections between the endpoints. And then there was a protocol called NCP that was sitting in the hosts and were connecting the hosts between each other. So it's completely different than the internet we know today. It was obvious that this was not a final solution. And all over the world, people started to think about better solutions. And the first who came out with a much better idea to do that was Louis Pouzin in France. He worked for IRIA, now called INRIA. And he built a network called Cyclade in 1972. And this was really the first network designed as an inter-network. Actually, the first ARPANET was just a network. It was one single network. And the network that Louis Pouzin built was designed to become an inter-network connecting different networks in the end. And even more important, it was connectionless. He invented the datagrams, which we call packets sometimes, but they call datagrams. And he also, very importantly, introduced a layered structure, which was well known already in operating system design, and but was never used in telecom. And on top of that layered structure, he had a transport service, which was residing in the hosts. He also very much pressed the importance of having names for hosts and applications, and not just for interfaces. This was, of course, fine, and the world agreed that we need to collaborate to find something that will be worldwide. And in '72, they started what was called the International Packet Networking Group. called the INWG. And this was started at the first ICCC conference, which was for international computer communications conferences or so. And there the people really started to work on the internet. And they produced a number of documents. So there was a document from Poussin, there was a document from others like Zimmerman, etc. And also Bob Kahn and Vint Cerf participated in that activity because Bob already worked for ARPA, and in '73 I think Vint Cerf joined, and Vint also became the chair of the INWG in '73. In '74, both Bob and Vint produced an article in the IEEE technical, the transaction of communications, called A Protocol for Packet Network Interconnection. And that document described TCP, not yet TCP/IP, TCP. And that was input actually also for this group. But of course, the views from the different participants didn't align immediately. That's normal, of course. But in this case, consensus building was rather difficult. But nevertheless, they succeeded in December '75 for a joint document called INWG 96. And Vint was one of the editors of this document as well. So this looks very fine. They had an agreement how to build a packet switch network for internetworking and connecting computers and researchers. And this INWG work was to be continued in ISO, TC 97, subcommittee 6 and 16. Initially, there was just committee 6 for data communication, and they created an additional one, 16, for open systems interconnection, it was called. That's where you see ISO, OSI appearing. But also there was still the CCITT, which was the collaboration of all the PTTs. And they also wanted to build networks, of course, for data communication. And so this all looked fine. Everybody agreed that there was a common consensus view how to develop these networks. And most of the participants, nearly all, agreed to work on the basis of this INWG 96 document. But then, big surprise, DARPA decided to continue along the lines of the 1974 publication. And that was a surprise to everybody. And the argument of DARPA was, okay, we have so much invested already in this network. And you remember, DARPA was set up to create a network, not just to do research and science. So there was some logic that they wanted to build the network, and in their view, for a limited set of tasks, of course. However, building that network wasn't that simple on these new specifications. Only in 1980, after 4 versions, that's why we have IP version 4, they considered it good enough to become the new ARPANET. So all the time we still had this connection-oriented ARPANET alive. And then in '83, ARPANET finally switched to TCP/IP. So that is the actual birth of the internet as we know it today, '83. And the 1st of January was called Flag Day, and they moved over. And in '86, ARPANET, which was of course dedicated for researchers with a research contract with ARPA, became broader, more universities connected it, and they decided there's a new infrastructure, a new operator needed to do that, and that became the NSFNet. And the defense part was already split off from that ARPANET before that became MILNET. Some of you may know that. But in 1986, NSFNet started, but also we got the first congestion collapse of the internet. It completely stopped functioning. And Actually, this was predicted in advance. I will show you what happened in a moment. What went wrong? ARPANET was set up for this small closed user group of researchers, actually to give them terminal access to remote computers, that's all. And the whole protocol stack and also the initial TCP/IP stack was focused to service that type of use. TCP/IP was actually much more powerful transport protocol because it was based on the work that was done in the INWG together with European and Japanese and other researchers. And during the development, which took 10 years, of course, of this TCP/IP protocol, they were still using the old ARPANET, which was a connection-oriented network, and TCP/IP worked fine over that network. But ARPANET was growing, as I just told you, so it was not only the original participants with an IMP subnet switch on their premises. New connections were being built who didn't have these connections, and they just connected directly their host to the ARPANET. And these hosts started to use TCP/IP only. They started to using the IP address, which was actually an interface address in this connection-oriented subnet, connected directly to the hosts. And this all worked fine, no problem, because it was simple. But by doing that, TCP had become the inter-network layer and the network layer. And you can imagine when they switched off the old ARPANET and the only thing that remained was the TCP/IP network, the whole thing became completely different. ARPANET had lost the inter-network layer. And because of that, it was not able to do anything about congestion control. If you see the hosts on the end of the network, and there's connections in between, and if something happens in the connection, and the hosts have to notice this and correct it, it will just take too long. You cannot manage these controls if your round trip time from the endpoints is much larger than the round trip time of the accidents happening in your network. In the old ARPANET, it was not a problem because the IMP subnet was a reliable connection-oriented network and solved all these problems before the host saw them. But here, it collapsed completely. But then you say, but so what? ARPANET, as well as the resulting NSFNet, were still actually prototypes. Everybody agreed that. For a limited group of research organizations, for a limited set of tasks. So, okay, in the end, we will have a much better solution and everything is solved. The internet would be replaced by networks based on this international protocol. And the know-how for that was there. Actually, TCP/IP, as it originally was designed, was okay. But only if you keep the network layer alive, which they didn't, of course, in the end. So they saw this TCP/IP infrastructure is just needed for a small period of time. And even the people in the US believed that. Everybody, also the NSF people, they believed that, okay, ISO, CCITT, they will deliver the future network that we need. However, international standardization efforts produced too little, too late. TCP code became freely available. It was free software. It started to be used by networks everywhere, in particularly local area networks. Universities all over the world started a local network. You couldn't connect it to anybody else initially, but you had your local network. And in particular, if you had a local area network on a LAN, high-speed local infrastructure, like the AMS-IX is doing, congestion is not a problem. So everything worked fine locally. But the networks emerged into the global internet we have today, because they started to connect to each other, point to point, and then via exchanges, and also over wide area connections, which were very tiny and very expensive at that time. So even if there were bigger pipes available, you couldn't even afford to pay for that. And you can imagine what happened. It was starting to be used for things it was not designed for, and the protocol suite was not capable of dealing with that. And of course, we saw this collapse in '86 already, and the first major patch was needed to continue because it simply started functioning. And the first patch really was the von Jacobson algorithm, which actually defines a slow start of your connections. And only if you reach the maximum of your capacity, you will give a signal that the sender has to slow down. And then, so it oscillates between half of your capacity and the congested network. But the problem, as I already said, it's even worse. The end-to-end points are so far away sometimes, and so even the signal from the receiving host to the sending host could be dropped because it's not a reliable network in between. So the whole thing was, of course, not stable. Let's look at some of the major flaws. Wrong addressing model. As I already said, in the internet, the IP address is referring to an interface on a host or a network. Nothing else. Because that's coming from the original ARPANET. In doing that, of course, let's continue first. As I already said, the wrong congestion control, and I already explained that is absolutely a disaster. But in addition to that, I didn't talk about it yet, the ARPANET was for a very small group, with a limited set of functions, and it had no security mechanism, because computers were very tiny at that time. They couldn't do much, and people were friends, they knew each other. Security was a non-issue, so nothing in the design took care of that. As a result, it's very difficult now to support multi-homing, because if you see that the IP address is an interface, if you connect to two different networks, you have two different IP addresses. If one of these addresses fails, how do you know that you can reach that host via another network? Because the host is unknown in an IP network. The only thing you know is the interface. You don't know the host. You don't know the application. So all kinds of tricks were needed to survive in that environment. Mobility is, of course, also a problem. If you go with your phone from one access point to another in your Wi-Fi network or your GSM networks, somehow tricks are needed to keep the connections alive. Quality of service was not a design parameter either. It was just best effort, still is. Difficult to support real-time and low latency applications was an obvious result of this, of course. IPv6 and network address translators actually complicated the situation even further. IPv6 was not a solution to the problem. In 1992, it was obvious that the number of IPv4 addresses was much too short for the world, because it was designed for a small group of researchers in the US. More addresses were needed, and at that time, 1992, although ISO was slow and CCITT, they had good solutions and protocols for real sound networking. For instance, there was a connectionless OSI protocol. And that was needed because the US wanted connectionless and Europe wanted connection-oriented. And so both were developed in the process. But at that time, IETF considered going for something that is invented by ISO is not what we need, because that would be incompatible with our IPv4 network, and we want to have something that is upwards compatible. Okay, 6 years later they settled on IPv6, which is not compatible with IPv4. So this is a real missed opportunity in 1992 to fix the problem that was created by the switch from ARPANET to TCP/IP. Okay, and what also is happening today is, and we learned it already from Henk, the internet is used for voice and for streaming video. Well, it's obvious that voice and streaming video have real-time, low-latency requirements, which is not a parameter of the current network. So again, you need all kinds of tricks and patches to solve that problem. Actually, most of the voice is not running over IP, but under IP to solve that problem. So complex patches were needed and are constantly needed still, because the network is growing, the type of users are changing, and for every change, actually a patch is needed to keep the internet going. So thanks to engineers, we survived until today. They did a remarkable job to get the internet going, and they still do. I don't know how long this is going to happen, because it's obvious that the current internet is not future-proof. Why were ISO and CCNT not able to fix this? Because in these 1975 results from the INWG, all the correct solutions were available. Actually, TCP/IP, as it was designed as an inter-network protocol, would have solved the problem as well. They made it both an inter-network and a network protocol, which meant that it was just a network protocol and not a reliable one. So it is very strange that ISO and CCNT couldn't fix this. Well, the reason for that is very simple. It turned out that all the major players from that time, the PTTs, IBM, which was then a dominant computer manufacturer, the other computer manufacturers, several mini computer manufacturers became important as well at that time, and the governments, they all had conflicting interests. The PTTs wanted to stick to this network that had the services included. They wanted to keep that on themselves. And they also only wanted to support connection-oriented network. Their thinking was lines, and a connection is a line, of course. So their model needed to be connection-oriented, and in Europe, actually, everybody supported it because PTTs were government-owned, and so everybody in Europe needed to become connection-oriented. IBM had a hierarchical network infrastructure called SNA, and they didn't like this openness and flatness, and they just wanted to have something that fits in their model. The mini computer manufacturers at the same time were friendly for the new type of networking because it would give them a chance to become relevant themselves. And also they believed that connection-less was the right thing for their computers, which it was, still is. And the governments, well, at that time, the whole landscape was very national oriented. You had your national PTT, you had your national telecom equipment providers, and everybody wanted to protect their own turfs. And then, of course, we had this big clash that the US government decided on the connection-less OSI stack. Europe decided on the connection-oriented OSI stack. And we were then stuck with the problem, how do we connect these two? So it took us quite some time to be able to prove that a connection-less network stack cannot connect to a connection-oriented one. So building a gateway in the ocean was technically not feasible. Well, that was really the nail in the coffin of the OSI networking at that moment, because before that, the US government made all equipment manufacturers obliged to support connectionless. In Europe, they were all obliged to support connection-oriented. But we proved that you could not make a worldwide network out of that. And the only thing that worked worldwide at that time was IP, thanks to over-provisioning. So the problem was very slow and resulted in overly complex solutions with too many, sometimes conflicting options, as I just explained. And it was not just the connection-less connection-oriented, but also everybody had their own wishes, and to make progress, all these wishes were included as options. And then the problem was, of course, by building the new equipment based on the new agreed standards, everybody started to implement their own wishes, their own options, and interworking was simply not possible in the beginning. And it simply took too long. Also, the PTTs failed to provide enough data communication capacity to serve the need for the computer networking. Already in the early 90s, we were moving outside the capacity of the X25 networks. Actually, in SurfNet, we had first-class X25 switches, which were used by the PTTs all over the world to serve their public data networks. And we had 2 megabit leased lines at that moment to support that. Turned out that our switches could not have more throughput than 380 kilobits per second. So a 2 megabit line was just waste of time and money, you could say. But we were allowed to use TCP/IP on top of the X25 network, which worked fine, as we already know. The need for higher capacity was immediately creating capacity problems in our X25 switches. The PTTs had no problem with that, because the only thing they supported was some users to have terminal access to a mail server or whatever. But we had real users, and it just collapsed. So that's why already in that time, early 90s, we had to split our 2 megabit lines in a T1, which we connected to our Cisco router, which became native IP, which was against all government and European Commission regulations. But of course, we proved that it's the only way we could serve our users. And we were allowed to do so. So we had, at that time, a real native, you were there, Henk? Native IP network in the Netherlands before anybody else in Europe at that moment. At the end of the 90s, same problem. We were using the ATM networks of the PTT, KPN by that time, and they saw that ATM would solve all the problems because it was connection-oriented, and you could have whatever you wanted to support your TCP/IP, etc. But even that was not enough capacity. So they could not support the gigabit connections that we needed at that time. And that's why we moved from, as David already said, or you was it, Henk, we moved from directly towards 10 gigabit connections, the router. We got beta switches from Cisco, beta routers, to connect them directly to 10 gigabits, and it worked fine. After we debugged them, and they all replaced them by new routers. But they were fine to do that. This was real collaboration between Cisco and British Telecom at that moment, who provided us with these fibers to upgrade these capacities. So, as you could see, users were left in the cold and started using what was freely available, first locally, finally worldwide, and TCP/IP won the war. And as I said, it really was the end of the war when we proved that interconnecting connectionless and connection-oriented network on a worldwide scale was impossible. I think it was 94 or so, Henk. Yeah. So what role played the Netherlands there in the development? Our contribution was very much user-driven. We didn't have, at that time, a real telecom industry like France, UK, Germany. So we were more interested in serving our users than serving our industry. In 1982, EUNet started with a central node at CWI here in Amsterdam, which was not an IP network at that time. It was a Unix network. It connected the Unix computers all over Europe via initially acoustic modems and later illegally real modems. And then an important date, 25th of April 1986, .nl was assigned to CWI, which was, I think, the first country domain that was assigned worldwide. By the way, this was the day before Chernobyl. So if you look April 1986, you will get Chernobyl on your website. In '86, SURF, which was the cooperation of the universities in the Netherlands, provided seed money to start RARE, which was an association of European research networks, which is now called Géant, and they have their office now next to the Balmer station. And RARE offered a home to kickstart E-bone, which was mentioned, the first European backbone, as well as the RIPE NCC, because that also started as a loose collaboration, but needed a firm footing in the end. And so the initial years of the RIPE NCC were hosted by RARE, and before they started their own organization. 17th of November '88 is another important day. This was the day that CWI got connected status to the internet. Before that, you could run TCP/IP locally, but you were not allowed to connect to the NSF net. And CWI was the first open connection to the NSF net. All other connections were only possible if you were part of the research arena in the United States. So the Netherlands was first here again. And this all was possible because the Dutch government took a very pragmatic position. As SurfNet, we were allowed to serve our users, and we were committed to go to the OSI solution because that was mandatory by the governments. But they realized that as long as that is not there, the users should use what is available as an interim solution. As I said, even NSFNet was considered an interim solution in the United States. So because of that, we were able to be at the forefront of the developments. And the PTT in the Netherlands was also very cooperative. They were open for experimentation, also for international connections. And this is one of the reasons that the AMS-IX could flourish, because we were able to get connections via the PTT to most of the places we wanted to go to, which was not something that you could do in many other countries at that time. And also they were flexible to allow SurfNet to build their own network, private lines, although they had a monopoly and could forbid that, and they were more seeing us as market development parties, and we took, of course, advantage of that. So we were able to experiment with private X25 network, E-bone, that the PTT, as a result, was then already contracted to provide a private X25 network to connect European research networks, which was at that time actually illegal, impossible to do that. You were not allowed to make connections. Only PTTs were allowed to do that. So they got an agreement in the PTT arena to offer that network to us. And even there, they saw this interim solutions. In the end, we were supposed to start using the public networks again. But as I already told you, the public networks are not capable of supporting us, and they never were able to do that in the end. And then, Henk didn't mention NICHEF, but I will do it. NICHEF and SurfNet started exchange points in Amsterdam, next to each other in different buildings, and this allowed everybody to make 2 connections to Amsterdam. We made sure that they were well interconnected, and this already gave some resilience there. And this is actually the birth of the Amsterdam Internet Exchange. And as Henk said, in '97, we formally incorporated this association, and I was one of the people who were able to sign the M6 in existence. So what's the conclusion of all this? TCP/IP brought us a wonderful internet. We wouldn't survive without it anymore. At the same time, it's obvious that it is no longer fit for purpose. A new architecture is needed sooner rather than later, obviously. So let's do something about it. And it will not be easy because there's a lot of vested interest, as you saw in the INVG, in the OSI arenas. To get consensus on protocols is not simple. And in this case, it's actually an open heart operation, because whatever we put in place for TCP/IP, you have to do it while the internet continues to function. So the transition, we have seen this with IPv6, the transition didn't even start. And actually, the nuts, I didn't mention that. Because there were not enough IPv4 addresses, you had these network address translators. You could have your own addresses locally, and then just one or a few addresses to connect to the rest of the world. And of course, after IPv6, the nuts wouldn't be needed anymore. But what the nuts did, in addition to providing more addresses, was hide you from this unreliable, unfriendly internet, which became more and more risky to be on the network and open to all your connections. Because in the internet, it's a flat space, it's a network worldwide, and every interface address is allowed to talk to every other interface address. That's the default. So nuts were a protection. So instead of throwing away the nuts because there were plenty of addresses when IPv6 came, the nuts survived, and they still survive today, and the transition is still very slow. And as you see my view, actually IPv6 transition is not needed because it will not solve the real architectural problems. Of course, it provides you with some additional addresses, but nuts will do that as well. And multi-homing, of course, will not scale. Mobility will not scale. We'll have to do something real. So if you're interested in helping solve these problems, I have a number of references where you can find a bit more background of what happened. And also, in particular, John Day's book, Patterns in Network Architecture, is worthwhile reading how the internet was developed. John was both working in ARPANET and he was working in the OSI reference model activities. So he was there when the folds were made. Okay, I think this is my introduction of the past and the future of the internet. I cannot predict you how long this will take to be solved. The only thing I can predict is that if we don't solve it, the next collapse may be the final collapse. We should not risk that, I think. Okay, questions?
Oh, we don't have time for questions because there's like pizza there. Yeah, so if you want to ask any questions to Kees, are you hanging around for a slice of pizza?
Yes, I do.
Great, amazing. If you have any questions, talk through a slice of pizza. Hopefully it'll still be warm. If it's not warm, we have microwaves, so we will nuke it until it's warm. Yes, if everyone could like stack the chairs in that direction, we have loads of space, and that'd be amazing. We're not out of beers. I need to go and get some more of those, but pizza is priority because Domino's is too efficient. They get it here early. Yes, thank you everybody for coming. Thank you for the speakers as well. They, yeah, highly entertaining. Very, very cool. And then, yeah, we're back in March with like a normal kind of schedule. Okay, thank you.
Thank you.
Thanks.